Okay, please be seated. I open the meeting of the doctorate committee for the PhD defense of Prasoon Garg and ask the PhD candidate to take your place behind the lectern. You ready? In that case, I would like to ask the first promoter, Professor Willems, to start the opposition.
Geachte promovendus, could you please summarize the work of your PhD project in the upcoming 10 minutes?
Answer your question with a small presentation. Have you ever imagined how much time does it take in the development of the control software of the engines, which are used in the cars we drive daily? Let me give you an example. It can take up to 4 months of expensive calibration time, out of which 2.5 months is of expensive testing and 1.5 months of expert time. Moreover, these systems are required to be robust against the variations in the environmental conditions. For example, the fuel economy should be maximized not just in the warm regions, but also in the colder regions. Not just at the sea level, but also in the mountains. Moreover, the complexity of these systems is increasing exponentially to develop clean and green powertrain solutions. Therefore, with the existing control software development methods, minimization of the development time and achieving robustness is becoming more and more difficult. And in the near future, it will become infeasible. Now let's dive one step into understanding the development process for the engine control software. The automotive industry follows a typical V development cycle to transform a concept to the launch stage. In this V cycle, the calibration process is one of the most time-consuming process, and it can take up to 60% of the time. Now let's try to understand what is a calibration process. A typical engine control system consists of a control software, which includes multiple maps and models. Calibration is defined as determining the best settings of the parameters in these maps and models such that the objectives listed here are achieved. Now that we understand the problem, now let's look how I address them. In my research, I have investigated into artificial intelligence methods to develop new advanced control calibration methods to minimize the calibration time and achieve robustness of the control system. In the last decade, AI has gained a lot of attention as more and more data is becoming available. Also, it has shown capabilities to learn complex patterns from the data. Also, it opens doors to automate the process, which you can expect can reduce the expert involvement and also calibration time. However, there are multiple challenges that needs to be addressed before these methods can be applied in real-world applications. Here, safety is one of the biggest challenges with using AI. Moreover, there is limited studies which actually quantify the benefit of using AI for reduction of calibration time and robustness of the system. These two reasons are partially the reason that automotive industry is a little hesitant in applying these methods on engineering applications. In my research, I have tried to address these challenges to unleash the full potential of artificial intelligence. As a first step, I have developed a method to minimize the number of parameters in the controller. For this, I have developed a long short-term memory neural network-based controller for transient control of a diesel engine system. However, calibration of these neural networks is a very challenging multi-objective optimization problem. The existing works, they mainly focus on minimizing the model error and minimizing the fuel consumption. However, they tend to overlook the practical elements such as the appropriate model complexity and impact on calibration time, which makes the implementation of these methods difficult on the vehicle. In my research, to address this challenge, I propose a novel multi-criteria calibration approach where not just the model error and fuel consumption are optimized, but also the model complexity and calibration time are optimized. As a result of this approach, the model complexity can be selected systematically such that these can be implemented on the real vehicle. Now imagine if this calibration process can be automated. To do so, I have developed a reinforcement learning based intelligent controller, which can autonomously interact with the vehicle system to calibrate the parameters in the control software. To do so, I have developed a novel exploration method that performs a safe learning on a real system in a time efficient manner. Moreover, it doesn't require models, it's model free, and which already saves significant calibration time. Also, this method is robust against the variations in the environmental conditions. Due to the novelty of this method, we also filed a patent at the German Patent and Trademark Office based on this method. I have validated this method on a real vehicle on a test bench and under different ambient conditions. You can see me sitting in the car. I, of course, did not give any information to the intelligent controller. I was just observing how it's operating. Now let's look at how it works. The intelligent controller starts its learning process by taking a safe action, and then it incrementally takes other actions in a safe manner, while parallelly also making a model of the efficiency of the system. By the end of the learning process, the intelligent controller knows which actions maximize the efficiency of the system. With this method, I've automated the calibration process, reduced the expert dependency in the process, and reduced the calibration time significantly. Now I would like to reflect back on the outputs of my research. Using the power of data, I have made significant reductions in the calibration time. As you can see, up to 70%, which reduces the effort from 4 months to just 1.2 months. Also, I have demonstrated robustness of the control system with the method under varying ambient conditions. Also, this work is one of the few works to actually quantify the benefit of applying AI for powertrain control in terms of calibration time and robustness. Also, I have developed a systematic calibration approach to select the model complexity which can be put on the real vehicle. Finally, I have developed an automated calibration approach using Safe AI, and I have demonstrated that on a real vehicle. With this, I would like to close my presentation. Hoe klaar de promoter? I hope I answered your question sufficiently.
Thank you for your clear and colorful presentation. Thank you very much.
Okay, the Eindhoven University of Technology is always very happy when external experts participate in PhD defenses. Today we have a number of these experts. Online, I would like to welcome Professor Jacques Bhakdi from the University of Alberta in Canada. Welcome, sir. In the room, on the other table on the left, I would like to welcome Professor Grafdal from NTNU in Norway. Welcome. Let me also introduce the other committee members. In the middle on the other table, we welcome the co-promoter, Dr. Silvas. On the right, Mr. Putz from Denso. And on this table, well, I already introduced the first promoter on my right, and on my left, we'd like to welcome Professor Antunes, also from Mechanical Engineering Department, and today also the Secretary. And my name is Patrick Anderson. I'm Dean of Mechanical Engineering, and it's my pleasure to chair today's session. So we continue now the opposition with Professor Shagbakti.
Coactive, do you hear me now?
Yes, we hear you now. Thank you.
Excellent. Coactive Pomendes, it was a pleasure to read your thesis and then see the works you have done. Especially, this is a very complex problem that you try to solve, and then you have looked at it from the eyes of industrial applications. So this was really a pleasure to see that one. And the systematic method that you have developed and effectively reduced calibration is definitely a good contribution to the field here. I got 3 questions, and then I would say 2 of them more is on the conceptual level. I will go one by one. The first question is, when we are talking about this engineering system, is very unusual that we have no model. We typically have some physical models from them, and then we know those models are not accurate. There are some areas that they need to improve. And then you are familiar with the notion of adaptive control. That also relies on the data and learning. So what you do is that you have a model that's captured a portion of that physics. And for the portion you don't know, you have this uncertainty term that over time you learn it, and then you will remove that uncertainty. And then in that field specifically, there are 4 decades of the works being done. And then now we have your methods that is trying to do a controlled it's still using the data, but in a different way. So if you compare your method with that 4 decades of the work being done, where do you see your method is going to excel compared to those, I would say, conventional adaptive learning methods?
Khelarde, opponent, thank you for your question. I believe, you mentioned about the existing methods on the adaptive control, and that they assume that there is a prior model. Maybe it may be not, let's say, very accurate, or it captures all the variations. But I believe that, first of all, I believe that having models for, let's say, complex systems like, in our case, thermal system, having models that capture so many, let's say, so many variations in a thermal system. First of all, I believe it's difficult to have such models beforehand. And what I mean to say is, I would like to elaborate there. For example, a thermal system of a vehicle, it operates under different operation modes, and it is subject to a lot of disturbances such as ambient condition, driver demands, and some unknown disturbances. So I feel that having prior models for capturing so many variations is difficult, or it will be a challenging job already to have prior models capturing so many variations. So I think there my work, which can learn in new, let's say, new operating conditions, it can learn the data. So I think there it stands out, because we don't need to, let's say, generate those models beforehand.
Okay, yeah, this needs maybe even more discussions, because it depends on the application by application, and because we have the systems running in industry, it's not that we are starting it from ground zero. So there are models available for them, but so it will become more to me on the space of that uncertainty. How complex would be that uncertainty, and how many dimensions will be there, and then whether these new methods you propose will be outperforming them or not over there. Maybe for the sake of time, I will go to my next questions. So this one is more related to, again, other methods that we see in the industry and also in the academia. And that's more related to the model predictive controls. For model predictive control, there is about, I would say, half a century of the work being done in that domain. And then MPC has also developed over years. The variance of MPC we see today is very different than the versions we have. And then we have also these learning-based MPC, that the ones that the models can be also being learned from the data, which has some elements in similar to your works, that is learning based over here. And then, so if you compare the new variants of MPC, that they are learning that happens, that you can use it for developing a model. You can have a model even for the disturbance and then embed that one inside the MPC. Where do you think your methods will stand compared to MPC, knowing MPC is also quite effective by considering constraint, whereas in your methods, yes, you have tried to do a safe learning, but then it's needed to go a lot of, I would say, gymnastics to be able to make sure that those constraints will be satisfied.
So thank you for the question. What I have understood with, let's say, learning-based MPC is that the MPC is mainly used there for satisfying the constraints. And then the learning part is done by a reinforcement learning, for example, using a reinforcement learning algorithm. And in that sense, if we're using only MPC for satisfying the constraints, in that case, my work can be put side by side, because I also I also have a safe learning method now, and which also learns the model safely, but also learns the control policy at the same time. So if MPC is only being specifically used to just satisfy constraints, then I believe my method is at par with it, because it also does the safe learning. Does that answer your question?
Correct. So there are so many different variants of the learning-based MPC that happens here. One of them is based on what you mentioned, that you will use the reinforcement learning, and on top of that one, you will utilize MPC to make sure the constraint would be on the safe set here. That one you don't have a proof because you don't have the comparison in your thesis. But then, so that would be maybe a future work for the people to look into it. But then there are also other methods in the learning-based MPC. An example would be that the model that you use for the plant, then models can be also learned from the data. That can be offline learning, can be online learning, and then that one being used inside MPC. That's one variant. The other variant is that the optimizer that you use for MPC, that can be also learning-based. Some of the techniques of machine learning being used in that domain here. So let's say for the type that you have the model that can either learn online or offline. So for that category, what do you compare? How do you compare your the MPC that the model is coming from the online or offline training compared to your method?
Thank you for the question. So in MPC, when we talk about MPC, we do assume we have a model, a prior model. And then there are some, for example, let's say if it is parameterized model, and we try to learn, let's say, true values of those parameters in the model. I think if I now talk about my work, there we assume no prior model information. And we assume that it can, let's say, build the model from scratch. So I think there I see a delta, that in terms of calibration time, the effort to make those prior models is already eliminated, because the learning algorithm I propose can start from scratch.
Are you sure about that one? Because what happens, because I mean, in my group, we have done both RL, we have done MPC, we have done all different variants of this one, and also I would say some of them very relevant application as yours that you have done. So what happens for your reinforcement learning, that exploration stage can also be quite time consuming, that the training you need for the exploration. Then the same, when you do these models, if those can be done offline, then you have some computational resources that you can use them. So it's really hard to say that the amount of time you need to put on exploration, effective exploration, would be less compared to the time that you need to have the learning of that model that will be used inside MPC, unless you have a proof that will kind of compare them. Yeah.
I agree with you there. I think because I have not done myself a one-on-one comparison, I do agree. I think that should be, let's say, a future work to actually try this and compare the calibration, as you say, if it reduces the calibration time. So there I agree with you that is an unexplored area. But as I mentioned, with this learning-based control, we are learning the model and control policy at one time. Also, we reduce the expert involvement, which I would expect with MPC will be larger than the method I proposed. So I think taking into account that expert involvement effort as well, I think, yeah, as you say, we have to test that out in the future work to see if that balance is out or if either one is larger or smaller. So, but I do see some gains in expert involvement and yeah.
Sure. I got only 3 more minutes, so my last question would be: I noticed the works you have done again is a great amount of work being done, and then it's definitely good contribution. Some of them are quite limited with the steady state, whereas in engineering system we see a lot of transients. So then what happens is becomes the question, we are talking about the engineering system that they have transients. We talk about calibration that always involves transients, but the message being proposed is more steady state. It's completely understandable. Not everything can be done in one thesis. So then what limitations from your work need to be removed in order to say that your works will be also applicable to the transient cases?
Thank you. I believe so. You are right. My work, if we talk about learning-based control, it was focused on optimizing the steady state, let's say, efficiency of the thermal system. I believe, and you are aware, I use the contextual bandits algorithm, which is doesn't take care of future impacts on the states. So I believe first thing would be to formulate, let's say, the problem as a Markov decision process. So that will be the first change I would make. And second aspect, I believe you're aware. So I use Gaussian process to estimate the uncertainty in the action values. And there I would expect, now that we have let's say optimize the transient operation, we would need some approximation which can capture time-based dependencies. And there I already see a link to my previous work that was on LSTMs. To optimize or to approximate action values, probably use LSTM networks, because you can imagine in a thermal system there are rewards are delayed, so you can see there are time-based dependencies. Additionally, I believe that not just LSTMs will be sufficient to get information on uncertainty. We will have to go in a direction of Bayesian neural networks to get the uncertainty estimates as well. So I believe it's going in that direction. If we want to capture or optimize for transient operation.
Yeah, thank you so much.
Okay, thank you very much, Professor Shabakti. Then we continue with Professor Grafdahl.
Thank you. Geachte promovendus, thank you for letting me read your thesis. I enjoyed it a lot, and but of course I have some questions for you. First, in chapter 2, there you have presented an overview of machine learning methods for engine control development. But that study it sort of stops in 2021, because that's when you published it, naturally. But as we know, this is a field in very rapid development. What can you say of relevant developments that have happened since during your PhD study on this topic?
Hukelar, opponent, thank you for your question. It's a very fair question. Indeed, as you mentioned, the chapter was published in 2021. I'll quickly go to that chapter. So in this chapter, I try to categorize the literature in similar to the classification of machine learning methods. That's supervised learning, unsupervised learning, and reinforcement learning. Since 2021, I believe that the applications I had for the supervised learning, those are using engine models as simulation tools for offline controller tuning, etc. I believe in supervised learning, they are still being actively used. what I feel is that now some modifications of, for example, neural networks are being made to accommodate specific processes, for example, misfire detection in combustion. So I'm a little aware that, for example, removing certain cells from the neural network to capture some, some processes in the combustion process. So I feel there is some field-specific development on the supervised learning side. Then I believe there is more attention. These methods are also becoming very famous for misfire detection, and especially their classification methods are becoming very famous for misfire detection, knock detection, which I felt was not that much used in, let's say, until 2021. I've also come across some applications of unsupervised learning, especially for data quality monitoring. And it is very, very relevant topic for the industry to detect drifts in the data or detect outliers in the data. So there I've seen and I've come across some unsupervised learning papers there, which I felt in 2021, that's one of the conclusions, that it is a relatively much less explored field. On the reinforcement learning side, and there I have seen quite a, let's say, exponential interest in especially for powertrain application. Relevant work is also from Professor Madi's team on diesel engine control for reinforcement learning. I think what I feel in the field is that they are trying to combine the good parts from control theory. So, for example, MPC, combining that with the learning, the benefits the learning brings in. So those methods I feel are getting more prominent in our field now, because indeed, that's one of the outputs of my work also, that you can do this learning also safely from scratch. Yeah. But I believe if you have a model, you can do some conservative learning in the beginning, but probably you have more confidence from safety point of view. And I think probably industry would prefer that. So I think those are the aspects I feel are explored more now.
Right. Thank you very much.
Yeah.
Thanks. I have some more detailed question regarding page 45 in your chapter 3. There you have a multi-criterion optimization problem.
Yeah.
And you choose your parameters D1 to D5,
yes,
such that these individual criteria have roughly the same magnitude.
Yes.
Can you explain the motivation behind that? My question is, are all these criteria, equally important? Why do you normalize, or why do you make them equally important like that? Isn't some of them more important than the others?
Yeah, thank you for your question. I fully agree with you, and I as a first step to develop this method, I did indeed give equal weightage to each of these terms, and I believe that these weights D1 to D5 indeed should be a designer's choice based on the application. So, for example, if let's take an example of memory complexity, that's J_MC. If I can imagine that could be a constraint for a real application, that you cannot have thousands of parameters of neural networks stored in the ECU, for example. So there I would imagine that you would weigh that larger than other weights. So I believe that's indeed a design choice that can be driven from the requirements of the system, or let's say requirements of the control system.
But in your work, you have used.
I have not played around with those values, but I am aware that indeed they are tunable and can be calibrated. Tuned.
Okay, thank you. And sort of on the same topic, then you go to bi-level optimization on the next page, I believe.
Yes.
I was wondering, how about local minimum? This is a rather complex optimization problem. There's probably quite a few different optimal solutions, or is there a problem with local minima that you? How do you guarantee that you end up in the good one or the right one?
Thank you for your question. I indeed made effort in addressing that. So I would like to point out to page 47, where I explored two cases, and that was the whole objective there. That so you understand that there could be multiple minimas in the loss, and indeed that was the observation that if I talk about case 2 first, that we only do the training once, but with the maximum number of epochs as a very large number. And what I could already see was that indeed there are local minimas, but if you give it sufficient training time, the loss converges after a point. So that is one way of let's say one way of making sure that you are not stuck in a local minima. However, I also found that this is very time consuming. You can imagine 6,000 epochs. It was taking me overnights to make these simulations already. So then I looked into something called early stopping using a patience parameter. And there I played with another parameter that's called number of runs. So I made multiple runs with different initial weights with some early stopping. And there I could already see that if you make multiple runs, there's a good probability that you end up close to what a very long training schedule converges to. So I did try to overcome that with carefully calibrating these hyperparameters.
Right.
I hope I answered your question.
You did. Thank you. Jumping a bit back and forth here now, but in chapter 6 on page 105, you introduced the concept of forward invariance. This is a term from nonlinear control theory, and at least it is used a lot there. And in that literature, usually that property of the system is proven mathematically.
Yes.
Can you elaborate on how you can guarantee that you're staying in the safe set, that your system is forward invariant? How can you guarantee it?
Thank you. So indeed, first of all, they do not formally give a proof that that safety is guaranteed. What I have tried to do with this safe learning process is that there is that an assumption can be made that there is a safe initial action. And what I have tried to let's say in a way try to be inside the safe set is that whenever using the information from the barrier function, whenever it tries to go towards the unsafe boundary, or let's put it the other way, if the agent feels that the action with larger uncertainty or more information is towards the unsafe boundary, it approaches that region slowly. So I have not, let's say I have not given the formal proof for that, but I have tried in a way that it never approaches the safe boundary very quickly or in a fast way. So what it does is it slowly builds around the safe action. It never takes larger actions towards the constraint boundary. So that I understand maybe during dynamic, during transient, it could probably overshoot the unsafe, the constraint boundary. But I believe because I have a decaying step towards the constraint, I believe that avoids that.
Have you experienced that it reaches the
No, we did not.
Simulations or no?
Not in the experiments.
No simulations,
no.
No. So
I did not see that, but I could expect that it's a feasible case.
Yeah.
It's a possible that that if there's agent takes a larger action, and then the system, because it could also be from not so well calibrated feedback controller.
Yeah.
So we did not observe that, and also, especially with thermal system, the temperatures and pressures were not so jumpy, let's say, on the vehicle. So I think that's probably a special case, the thermal system, that temperatures increase slowly. So we did not see that actually.
Thank you.
But
So, Professor Gafdala, you're happy with this discussion so far?
Yes, I am. So,
Yeah?
Thank you.
Okay, then I would like to thank you very much, and then we continue on this side of the table with Professor Antunes.
Geachte promovendus, I'll start my questions with chapter 5. So there you start with a very general framework of doing safe reinforcement learning, but I have the impression that as you move along this chapter, you make more and more assumptions tuned towards your application. So I want to understand where can we draw the line between the generality of your method and actually the assumptions that you make to make it proper for your application. In particular, is your method applicable when the action space is Rn, or is it just applicable when it's R?
can you repeat the last sentence?
So the action space, is it Rn when n is larger than 1, or is it just R?
Zeer geaarde opponent, thank you for your question. First of all, it's just one-dimensional action space.
Exactly.
So
So you
it's
start
only
with
R.
the general framework, but then your method is only applicable here. But then the constraints can only be very simple, or am I wrong? Is it like your variable, which lives in R, is upper and lower bounded? Those are your constraints.
Yeah.
Okay, very well. And then you exploit this by providing a method that if you go to page 78, please. So you first explore by picking 3 actions around some safe initial action. Well, an initial action and additional 2 actions.
Correct.
And then you say that then I can determine, you say it in the last paragraph there in the initialization, that as a result of this initial exploration, the agent determines the direction in actions approaching the boundary, right?
Yeah.
So how can you do that?
Because I use a reciprocal barrier function, which is a difference. Let me go to that. So I use this reciprocal barrier function where if you look into h of x, that's the constraint. Let's take an example of upper bounded. So x bar minus x. So as the system state x approaches x bar, the hx becomes smaller. And then the corresponding barrier function value increases as a logarithmic function. So you let's
say that you have that your boundaries are your variable in R is between 1 and 2, and your initial action is 1.5. Then you take an action in 1.55 and an action in 1.45. Can you know the direction? So I have.
I believe so. What I have seen is that indeed, if you let's say the delta around the safe action is also calibratable. On a real system with noise, if you take such small actions, indeed you cannot determine.
Okay.
I've also observed this. So with the noise, it is difficult. So I made that as a calibratable. So the delta small a, I made it as a calibratable, and we had to increase when we tested on the system to be significant so that we could actually see the impact on barrier function.
Okay.
So that is true indeed.
If you go to page 77, so one page before that one, if I understood correctly, the way you evaluate the outcome of an action is by averaging in those L1 or L2 seconds the outcome, right? And then you say that the outcome of that action is actually deterministic. There's no noise because you average.
Yeah.
And I wonder, why did you do that? Because for me, I mean, like, you are exploring the action space. So you want to achieve the optimal value of A as soon as possible. Wouldn't it be better to actually save that time or use that L2 seconds to sample a lot of actions.
Yeah.
And in that sense, reduce the variance of your Gaussian process as opposed to averaging and assuming that there is no noise.
I understand that in a sense that, so for example, it's a thermal system and the rewards are much delayed. So in that case, I would have to formulate this, of course, as a Markov decision process. And I think if I do that, then we can indeed make use of these rewards which we are getting during transient as well. So I think I limited let's say I limited the problem formulation to first only to contextual bandits. And there it would not make sense to collect delayed rewards because you can.
So it has to do with the fact that you have delayed rewards.
Yes, I think when you have systems with, yes.
Very well. Maybe a related question. So your choice of state in this chapter only contain two variables, if I'm not mistaken, so the ambient temperature and humidity.
And the demand cooling load, I think, yeah.
Okay. But then if I look at your plots, I think around page 90, I think 89 or something. If you go there, or actually 91, if you look at your plots, it seems that so is the optimal action then is, around 25, but is it for a given state?
Yes.
It's for a given state.
Yeah.
So it changes if
with
we
the
change
state. Yes. So state is one of the inputs to the Gaussian process.
Okay, very well. Moving to chapter 4. So there your state contains three variables, right?
Yeah.
And my question is, again, your action space is only also in R, I believe. And you use deep neural networks, deep reinforcement learning.
Yeah.
And I wonder, because you also discretize the action space. If you had discretized the state space, okay, it would be large, but not large enough to prevent you from using, for instance, a tabular reinforcement learning method, which has the advantage, to me at least, that would provide optimal solutions, because you can have, let's say, just Q-learning in tabular methods will provide you the optimal policy.
Yeah.
And in deep Q-learning, you're not guaranteed to find the optimal policy. So my question is, why didn't you use a tabular method and a method that would guarantee there in that domain optimality?
Thank you for your question. So, as I previously mentioned as well, the design space for a thermal system in a car is I think around 5 dimensional. Vehicle speed, ambient temperature, cooling load, relative humidity, blower speed, fan control, fan speed. All these create disturbance to the system. Existing controller, as far as I remember, is only capturing the effect of ambient air and cooling load. As a first step in this work, we wanted to see if we can improve efficiency, that is the COP, by introducing a new state, that's the vehicle speed. And you can imagine vehicle speed has great impact on cooling. So indeed, for only 3-dimensional space, I understand tabular could have been a good option. But our intention was that we could be able to scale this up to include also
for the future.
Yes.
Very well. By the way, in 4.8, why don't you consider this, the state to be, you have a reference state, the last one, but that is associated with an actual temperature.
Yeah.
Why don't you consider that actual temperature and you consider the reference in the state?
Yeah. Yeah. So this has to do with how generally steady-state control is designed in industry. Usually, if I give you an example of an engine control system, the supervisory controller is always giving out the demand engine speed and demand torque demand, for example. And then the low-level controller tries to satisfy that. So that is a very general industry practice to use in a supervisory way the demands and then try to satisfy that. So we try to keep that
the inner
interface.
And outer loop, exactly, the inner and outer loop or the hierarchical control.
Exactly.
that
To
you
keep,
explained. So you only worry about the first one.
because otherwise we will have to also modify supervisory control.
Okay, very well. Do I have time for one more question?
Yep, the question is short and the answer as well.
Okay. If we go to chapter 3, and you already have questions about this, I think it's page 38. You have a multi-objective problem, optimization problem, and there you pick 38. Are we in 38? Yeah, on top of, yeah, exactly.
Yeah.
So there you see the calibration effort, which is, if I'm not mistaken, is the second term, right? This
Correct.
one.
Yeah.
So you mentioned that it depends on the parameters. So I was a bit puzzled. Is it constant or does it depend on the parameters? And how do you determine that calibration effort?
So the calibration effort is dependent on the hyperparameters. And as I was previously, I previously mentioned, for example, how long do you train a neural network? That could have a direct impact on calibration time. So only the hyperparameters.
But can't you not only know these function a posteriori once you start training it, or not? Can you know these function a priori to put it there and optimize it, or how at the end of the day, what does it boil down to? I know you do an exhaustive search, so you only a posteriori, you say you pick some hyperparameters and say, okay, this was
among that, indeed. So in
the
that
training time.
In that range of hyperparameters, what minimizes that?
Okay. And related to my very last question was, so you also penalize here a cost of the model mismatch or not?
Yeah.
I think is the first one. So, but that's not your goal. Why, if you use a model-free approach, would you at the end try to tell the model-free approach, hey, look, I want the model to be good?
Please keep your answer short.
Yes. If I pick the main reason, it's also the explainability of the signals.
Yeah, that's enough. Thank you very much.
Okay, much appreciated. We continue with Mr. Puts.
Geachte promovendus, thank you for your presentation. I think you summarized well. I listed 3 questions, and the first question is related to chapter 3 and 5. You explained in chapter 3 an LSTM, which is capable of capturing transient behavior, right? And then chapter 5, you introduced reinforcement learning, where the current challenge is the steady state definition or the steady state validation. My question was, would be introducing an LSTM and a reinforcement learning framework a logical next step? And you kind of already explained in one of your previous answers. So I will continue this question. So this could increase the complexity again of the system. Is there a methodology or a way to not to increase the complexity and deal with the transient behavior?
Thank you, Mr. Putz, for your question. I believe if I talk about let's say I think the alternative to LSTMs could be explored, because you are aware LSTMs are quite complicated. So in that sense, my next logical step would be to consider less complex approximations. So probably a multi-layer a static neural network with some inputs of some delayed inputs as well. I would expect they are less complicated than LSTMs. So that would be my first step, that I would try to simplify or use a simpler, let's say, machine learning model to capture the transient, let's say, the time dependencies between, the time dependencies. That would be my approach to answer that.
Okay. Thank you. So also maybe later we can discuss in detail in this. So it's thank you for your answer. My second question is related to the ratio of exploration and exploitation, where you introduced an efficient method, a Gaussian method, to explore the system. And in a simulation environment, you have proven the method of exploitation as well, and you found a performance benefit. What is still needed in terms of calibration efforts to bundle these two points in order to complete the complete system?
So if I understand correctly, you mean complete system as in including multiple actuators, or do you mean including all the variations?
Exactly. So not only for a specific single state that you use for exploration, but how to consider this data also in the total system, considering all the states.
Yeah. So I believe I think the current the approximation, the way I currently do the approximation, it's a function of states. So we can simply let it run on different values of S, that's the states. And the Gaussian process, of course, will get more complicated, but can handle all the state variations because it has been, let's say, modeled in that way. So I believe if we simply run it on different states, and in our case, those are ambient conditions. So I believe it can capture all the variations. It's the matter of running this in different states, steady state points.
Okay, understood. A last question. You explored the Q learning, WQ learning, the form of network. Is it correct understanding that we are using a tabular Q learning? It's possible to minimize the data needed in order to capture a certain behavior compared to introducing a Q learning in the form of a neural network?
Thank you. Very interesting question. My understanding is that if we want to fill tables, then, for example, if it is three-dimensional table with each the size of the size of each dimension is, for example, 10. So that's 10 cross 10 cross 10. That's 1,000. And what I remember from the work we did is that with the neural network we only required 500 experiments before error was quite small. So what I remember is that with the approximation, we actually even didn't need to export the full factorial to fill the table, but just less number of iterations was enough because the neural network could capture the nonlinearities. So I believe, and I think that is it's little difficult to say that beforehand. That if use neural network, it will converge faster. Faster. But that was the observation I had, and I remember that. Yeah.
Thank you.
Okay, thank you very much. Then the last couple of minutes are for the co-promoter, Dr. Silvas.
Thank you. So Prasoon, I have asked all my questions, detailed questions so far, but as you know, I always have more questions. So today I will look at next work, future work. And I was thinking for the figure you have on page 34, we put a lot of effort in modeling calibration processes. If you look at this figure, in your recommendation chapter, you mostly comment about the detailed methods and challenges that you encountered. But how would you extend this if the car starts having automated driving functions like lane keep assist, or you consider fleet information? Does the picture still hold, or where are the main challenges?
Sirklar, the co-promoter, thank you for your question. If I understand correctly, you mean that if we have to calibrate for a fleet of vehicles, are they connected or not?
Is there information when cars start becoming more complex in their software and you maybe get fleet data in your vehicle? Is there more information, or does the calibration process change? Or does it remain the same?
I believe some information from the fleet data could impact the effort we spend in optimization, probably. So what I mean is, if we can use the information on what is the most frequent operating conditions a fleet of vehicles or trucks drive in, and we are aware for trucks there is indeed a Rossi point where they operate more. So probably that type of information could be utilized in the optimization block here. Probably that could, let's say, divert the effort more in calibrating the regions which are more used compared to which are not so used. So I think there some information from the fleet data could be used. But I do not see any change in the way this new calibration process should be done.
So you're saying the picture remains generic enough, but maybe you have more information you can rely on?
Yes.
And there comes my next question. In the recommendation chapter, you say transients are very difficult and you will encounter more and more transient conditions when you go to real life operations, but still you could benefit by online learning. So my question would be, what do you need to monitor in the LSTM design or the RL design to ensure that your models don't drift, or that your operational data is too far from your learning data? Because in all the pictures you've shown us, it's mostly about the design phase, but you say we're also going to learn on the road. So that also touches on the monitoring part of your system. So what is important to monitor?
I believe if we, so you are right, the methods I have developed are to be used in the, let's say, in the controlled environment, where you could vary ambient conditions and control them such that the learning method can optimize parameters. When we go to on-road vehicle in a real environment, I believe, as you mentioned, it is indeed one of the challenges to know, first of all, which data should be used to update, which data should be used to learn. So I believe, I think in the transient data, or the data collected during transient, still the information content can be something that can be monitored, such that we look for the data which always tries to maximize the information content, which can be modeled using some approximator like we mentioned. So I think the similar concept of information content can be scaled up, and then that can be used to determine if which part of the data can be used to learn.
And you're thinking more about the input, so how much data are together and how complex this data is. Would you also monitor something about the models that you already implement in the design phase?
Oh, yeah. So I believe you refer to effects of aging, for example, that could vary with over time. So I indeed, so I do believe if you have continual learning on the vehicle, I believe that will keep shifting if there is indeed a change in the system characteristic. So I believe if there is continual learning happening, it will the models should automatically.
Okay, we have just learned that the hour has passed. So I would like to ask the doctoral candidate to take your place back into the audience again.
Thank you.
The committee will now withdraw for deliberation. This meeting is adjourned. Please rise. Okay, please be seated. I reopen the meeting. I would like to ask the doctoral candidate to take your place in front of this table. The Eindhoven University of Technology, represented by us as doctorate board, has examined your dissertation and heard your defense of it. On the grounds of the aforementioned, the doctorate board has decided to award you the degree of doctor. I request that the first promoter acquit himself of the duties entrusted to him. Please all stand.
Uit kracht van de bevoegdheid ons toegekend door de wet en namens het college van promoties bevorder ik u, Prasoon Garg, tot dokter en verleen ik u de rechten die verbonden zijn aan de dokterstitel. Ten bewijze hiervan overhandig ik u diploma ondertekend door de rector en de promotoren.
Okay, please be seated.
Okay, thank you very much. Still on? Yeah. Dear Dr. Garg, dear Prasoon, congratulations for you, Mansi, and also friends and family. I know also a lot of people are following the live stream, so congratulations to all friends and family also online in the live stream. It's great to see you here standing. It's fantastic, I would say, to reach this academic milestone in your career. So congratulations with that. And I do believe that this is a fantastic result of development. It's not only research development in that side, but it's also, I think, a huge personal development in your career. So I want to focus a little bit on those two aspects in this Laudatio. So to illustrate your journey, so 4 years ago, you have to imagine it was a Monday. It was March 2nd, 2020. I think it was a similar day as today, a foggy day, if I remember well. But then you, Prasoon, you just received your master's degree. You did your work in TNO. You were, I would say, a modest engineer. You were living in the Luna building, very close here, I think 300 meters from here. And just 3 weeks after Prasoon started, we got the intelligent lockdown in COVID. So a nice link to his intelligent data-driven systems, right? So a very intelligent lockdown. But look now how you stand here, 4.5 years later. I think very nice to see that development. You have your PhD degree in your hand. Prasoon went to different international conferences all over the world. But also very important, you're married to Mansi. You no longer living in Luna. You have a very nice apartment in Eindhoven, very close here. And you own a dog and an Audi A1. So I think all a person can wish for, right? I think you have the full picture now. So what a nice delta was that. So this is not coming out of the blue. To stand here and achieve this. So obviously it requires a lot of hard work, a lot of perseverance, but also a lot of eagerness to learn and to consistently improve. I think that's one of the key words if I think about your work during the last 4 years. And I think it was also very nicely summarized by the quote in his thesis, which I quote says, success comes by aiming at the target and not by aiming at the obstacles. I think that was also very applicable to your work you did during the last period. So if you only look at the output of your work, you had 3 conference papers, 3 journal papers, still some on the review, but very nice, but very special, very unique. It's not happening a lot. You also have 1 patent. I come to that later. It's not, you don't have it on your own, so you will not be the only who get money out of it, but there is 1 patent, so really great. So you can really be proud of that. But in my opinion, what really stood out is the demonstration of your developed learning methods. And I think it was a little bit maybe not so prone today, that was also part of your work, but I think that that's really something you can be really proud of, and that's also scientifically stands out. And you did a demonstration on the test vehicle at Denso in Wakeberg. Really nice. So to get there, to achieve that at the end of your 4 years, obviously that requires development of a mathematical framework. That was the starting point. How are you going to do this? What is the concept? How are we going to implement that? And what you learned during that period that was very important for you is, okay, how do I create space? How I do create inner rest to work on this more thought process. So that was really nice to see how you developed there. But by implementing it on the vehicle, there you make the difference. We also had a discussion in our committee, like, okay, there is still a lot of work in simulation, desk studies, but to really bring it to the vehicle in Wakeberg, that was really, really outstanding. So I still believe that this is a world first in terms of the reinforcement learning applied to this thermal management battery electric vehicle stuff and deal with this safety critical aspects, which is not unimportant because the vehicle should survive at least the testing phase. That would be the minimum you would expect. But in my opinion, that could not be realized without the collaboration with the people from Denso. And I'm very happy to already recognize, obviously, Ron Putz is in the committee, but I'm also happy to recognize other experts from Denso here in the audience. And during your project, you heavily invested in this partnership with Denso. And by continuously discussing with Ron, but also with colleagues, you try to understand the challenges. We had a lot of discussions today. Yeah, what is this calibration process? What is the current standard? And how do you improve on that? And by presenting your ideas and also your concepts, that made the real step forward. So can we bring across these ideas? And in my opinion, with that, you overcame one of the most underestimated obstacles in doing research, and that is basically talking the same language. So it's talking the same language in terms of, okay, you have to align with academia, academic experts, but you also have to align with the control experts and the control engineers and test engineers at the Denso site. So that was really a great job. You really did a great job there. But on the other hand, Denso brought focus. They said, okay, yeah, we go to work on a battery electric vehicle. It's very important that the batteries are at the specific temperature, because else, yeah, our batteries in our electric vehicles will not last that long as they should be. So in that sense, you also contribute to a very green and sustainable future. Very nice to see that. But to get it on the vehicle, one of the main contributions was also, okay, you need to code and get it work. So I already mentioned that that part was maybe underestimated and underlighted here, but I think that was really important in your work. And what Emilia and myself really enjoyed was, so the more it was going to work and you were working on the vehicle, I think also exponentially increasing was the enjoyment and the pleasure in your work. So I think that was really nice to see to the end of the project that really was going well. So, and with that, you demonstrated the added value of AI. You already mentioned it in your introduction, and maybe it's a little bit overlooked what is important about that. So there is a lot of discussion. We want to use AI, but what is the real added value in terms of also economical value? You put a lot of effort in that and show what could be the potential and the outreach to implement it. And I think the importance of your outcome was also recognized by Denso, because we jointly filed a patent on your developed method and also on how it's implemented. And I do believe that's a nice example of how and why Eindhoven University is still in the top rankings globally, worldwide, in collaborating with industry. So I think you also contribute for a very small piece there. So thank you for doing that. So that is the research development side, but also on the personal side, a lot of things happened during the last 4 years already. Give you a small glance on that. So not only technical obstacles. So in COVID lockdown, it was very difficult to have face-to-face meetings with Emilia, with Denso and myself. And I clearly remember you were living in Luna here, 300 meters from here. So we had Teams meeting, and then you were living in, basically you were sitting at the kitchen table in a one-person apartment. That was sort of your start. So a very inspiring environment to do research and come up with innovations. You can understand that. But more important, it took way longer before Mansi could come to the Netherlands and could join you here. And that I'm pretty sure that was not an easy period for both of you. So in that period, we learned that you were very determined and very focused in your spare time on working on your cooking skills of Indian meals, and also on dancing to Indian music. You told us a lot about that. That was a lot of time went into that during your spare time. And that made you probably, when Mansi was coming to the Netherlands finally after 1 year, you were very well prepared to take these duties. And we could notice easily, and we could easily conclude that that was definitely giving you a huge relief, I think both of you, and positive energy. We could really see that in your work and when we met you. But I think Emilia and I could also conclude that your dancing skills, your cooking skills, they must be outstanding because I would say within 1 year you married. So that must be the case. I mean, there you see exercise really worked and was helping you out there. So very, very nice. So it was great to see you find apartment together and also that you're now both rooted in this region. So that's also very nice to see that happened during that last 4 years. And in my opinion, that journey also illustrates that everybody is looking at the thesis always, and typically most people only look at the outside, like nice color, nice design, but this stands for more. It's not only a thesis, it stands for your academic and personal development. So I think people should not underestimate that part. So before I come to the end, I want to acknowledge also the contribution of various people in this project was called the Powertrain Brain project, because then we could do AI squared in the acronym. We really like that, so that was good fun. But first of all, I want to thank the entire Denso Automotive Germany team in Wakeberg for, I would say, their fantastic support. I think that was really amazing what they did for you and the project. And especially I want to thank Sebastian Visser. Very great that you are here today. I want to thank you for your enthusiasm about our research in self-learning systems in my group, but also that led finally to initiate this project and our strategic collaboration. And Sebastian, you're really a fantastic ambassador basically for whole university, I would say, in Denso globally. So it's quite fun that we have an ambassador like that. So thank you for doing that. And you also arranged a visit of Denso higher management, so of Ken Uchiyama and from John Lapierre to Eindhoven University in the fall of 2019. And that was also very memorable, but because we showed them around the automotive lab, so obviously they liked a lot of these nice student projects we have, including the solar team. But in my opinion, they were most excited of playing football against the robot soccer team and being the goalkeeper and try to avoid those robots to score. So that was really nice. Also special thank you to Ron and also your colleague Bart van Moergestel. I think he's not here yet, but both of you always made time for detailed discussions, for your support with the vehicle demo, also very important, but also to promote this AI project in Denso, because what is really happening there far away from Japan and the Netherlands on this topic. And it was great that you could also provide the enthusiasm we have on the project to your Japanese colleagues. So thank you for doing that. Also special thank you to co-promoter, your co-promoter, Emilia Silvas. It's a pleasure to team up with you. You support ideas and also your daily supervision. I think that were of great added value to the project. And I see already Prasoon nodding, so then it must be true. And also there, I think it was also very nice to see that you were inspiring sounding board, because you have similar backgrounds coming from abroad to the Netherlands. So what are the typical things you run into with those strange Dutch people? So also thank you for picking that role. So last but not least, I want to thank Professor Grafdal and Professor Shakbakti online for accepting the invitation and to participate in this PhD defense. It was a great privilege to have you as external committee members here today, so thank you very much for your time. So that brings me to the end of the ceremony. You're standing already too long, right? So I should summarize now. So Prasoon, you already found a job at DAF, so that's really cool to see, okay, there your knowledge will also sort of be cemented and see how we get it in applications. And I'm pretty sure that young and smart researchers like you will be the key to accelerate the transition to climate neutral transport, which is obviously very important. So it was a pleasure working with you. I also say that on behalf of Emilia, and we are pretty sure we keep in touch. So there's still publications to be done, so that will be at least the reason. And we wish you and Mansi all the best for the near future. And I would say it's time to celebrate now.
So, Dr. Garg, it's my pleasure to also congratulate you on behalf of the Doctorate Board of Eindhoven University of Technology and the Department Board of Mechanical Engineering. It's well, very nice. You can carry the doctor title now. Ask staff to update your business cards, change your social profiles, and you can do that as of today. But there are also some duties connected to the title, and they start today and last your whole life, and I need to read these to you. The scientific degree of PhD involves duties as well as rights. As a holder of this degree, you're committed to standards of scientific integrity, trustworthiness, intellectual honesty, openness, independence, and societal responsibility. These standards are described in more detail in the Netherlands Code of Conduct for Research Integrity and in the Eindhoven Code based on it. You also have duties towards society. You must be clear about the boundaries of your own expertise, and you must communicate honestly and independently about the results of your own work, including potential risk associated with it. You are committed to the ethical codes for research and design involving human subjects or animals. So with these final words, I would like to ask you to take your place back into the audience. So ladies and gentlemen, well, thank you all for attending today's defense. Let me explain a little bit the procedure now. After I close the meeting, we have a photographer who's going to take a picture of the committee, including the online member in front of one of the screens here. It can be one picture, multiple pictures. We'll see how that goes. After the picture taking process, I'm going to ask the young doctor to stand there and look at the screen in the back, where Professor Chakrabarty can actually say a few words to you. And after that, the beadle is going to escort us outside. And I would like to ask the young doctor with your partner to follow us outside, and then the audience can also follow us. So only at that moment we will start congratulating you. Okay, so with this, I close the meeting. So Professor Chakrabarty, you can now address the young doctor.
Okay, yeah. Dr. Prasoon, congratulations. Well done. It was a pleasure to know you, and then reading about your work. It was really a good mix of theory and industrial work. This is what we really don't necessarily see it in every PhD thesis here. So well done. And I just learned today that looks like now you are experts of the Indian food and dance. So have a great celebration with Indian dance and Indian food. I wish I was there, but then to shake your hands. Otherwise, I keep my opportunity. Maybe I will be visiting Eindhoven soon, so then we can talk more. Congratulations and well done.
Okay, thank you very much, Professor Chakrabarty, for these nice words, and we see you next time in person. Bye-bye.
Thank you.